variance is just the average of the squared differences from the mean. It's a good estimate for the variability from what's expected based off of a population or some sample you've collected. It's the summation of x minus x bar. How much each data point differs from the sample mean, x minus x bar squared. I have to square it because sometimes could you be more than the sample mean, above what you'd expect. Sometimes you could be less than the sample mean. So I want them to all be the same signs. We have to square both of them, so they don't just cancel out when I add them together. Take the differences from the mean squared, and then how do you find the average of something? When I take the average, what do I have to do? I'll divide first after I do what? Add them all up and then divide by the number of things you added together, right? Yeah. So I'm going to take the summation of all the squared differences from the mean divided by not the number of things minus 1, because we have a degrees of freedom based off of our sample size. Add all the squared differences together and divide by n minus 1 for sample correctness. Sample variance is the average of the squared differences from the mean. Because I had to square everything, the sample variance isn't measured in the typical units we were given for our data. It's measured in squared units. I had to square all those differences from the mean. So to put it back in more usable units, or how we commonly measure different from the mean, we have what's called standard deviation. Notation for standard deviation is S. S is the sample standard deviation. So if S squared is the variance, wouldn't it stand to reason that the sample standard deviation S is just the square root of S squared? When I square root a square, doesn't it cancel out? Similar notation for population variance and population standard deviation. Instead of S, we're going to use the lowercase sigma Greek letter. Sigma squared, lowercase sigma squared, is notation for population variance. And lowercase sigma, just sigma itself, is population standard deviation. The whole point of a confidence interval is to take our sample standard deviation and variance and use it to estimate the population. I only look at some of the population. How can I reasonably estimate the overall variance, or overall standard deviation? That's what our point is here today. Using chi values, how can we create interval estimates, taking our sample data for the overall variability, population standard deviation and variance? Okay, so chi square as a value comes from this formula here. Chi square equals n minus 1, sample size minus 1 for the degrees of freedom, times S squared divided by sigma squared. Chi squared equals n minus 1 times S squared divided by sigma squared. Can your variance, whether it's the sample variance or population variance, ever be negative? Could I ever be a negative distance from the mean? No. So shouldn't this value right here always be positive? Yeah. If I take the sample size minus 1 times the sample standard deviation S squared divided by the population standard deviation sigma squared, is that always going to be a positive number? Yes. Assuming that our population is normally distributed, this should be always a positive value, and it should follow a chi square distribution. Now let's compare this formula with what's down below. Very similar, but what changed?
Sigma.
Chi and sigma switched. What I've done is I've multiplied both sides by sigma squared, the population variance, and then divided both sides by chi-squared. These can just flip by multiplying and dividing by each at the same time. By multiplying each side by sigma squared, I cancel out dividing by sigma squared on the right. I have it over on the left. Now, how do I solve for sigma squared? How do I get rid of multiplying by chi-squared? Right. So sigma squared equals n minus 1 times s squared over chi-squared. Basically, these two are just interchangeable. A little bit of help. So we can kind of see that the population standard deviation, we can see that sigma squared follows a chi distribution. Sigma squared is defined by a chi-square value. We can therefore use a chi distribution to cut off certain parts of the distribution of our population variance. We can use a chi value to cut off certain parts of the distribution of the population variance sigma squared. Since it's defined in terms of chi, we can use a chi table to cut off certain parts of the distribution of our variance. So how are we going to do that? I have a chi distribution down below, defined by two different values, chi-square right, chi-square left. Why would this be chi-square right?
Because it's on the right.
It's on the right side, right? It's the right endpoint. Why would this be chi-square left? Obviously, it's on the left side. So in the middle, I have like maybe 95%. I want to have a 95% chance I've captured some parameter, like our population variance. Of course, there's some error. Error lives in the two tails. If there's 95% in the middle, what's in either one of the two tails? What would be in the upper tail on the right-handed side? 2.5%, right? Because don't you take your error, your alpha, the 5% chance that I don't capture it? If there's 95% in the middle, there's 5% chance I haven't captured it in the left and the right tails. I take that 5% alpha divided by 2. What's above this right-handed cutoff? The 2.5%. Now, since chi-squared is always right-tailed, what's to the right of my left-handed cutoff? I have to look it up using a right tail, or we're going to use a chi table. Chi is always right-tailed. What's to the left of chi-square left cutoff? Sorry, what's to the right? I said right. What's to the right of my chi-square left? Pardon me. Because there's 95 in the middle here, 2.5 here. So this is defined by 97.5%. A right tail of 97.5%. Which of these two values has a bigger chi-square score? Is the left-handed chi-square or the right-handed chi-square going to be a bigger number? Why right, Casey?
It's always positive,
so if I put 0 here, if chi is always positive, which one's further from 0?
right.
Right. Left would be some smaller chi number, right? So when I set up my formula, I'm going to take n minus 1 times s squared, n minus 1 times s squared, and then divide by two different chi-squared numbers to capture a certain part of the distribution. You want to have 95% in the middle, 99% in the middle, 90% in the middle. What type of confidence interval are you creating? How certain do you want to be you've captured the parameter? What happens if I take that value, n minus 1 times s squared, and I divide it by a very big number? If I divide something by a very big number, what happens? It's small. So if I want this left endpoint of the interval to be smaller than the right endpoint of the interval, no, I need to divide by the bigger chi number. That is the right chi-square right value. Even though this is the left endpoint in the interval, I need to use chi-square right value to make it smaller, because isn't this right-handed chi-square value bigger than the left-handed chi-square value? You take a value divided by something that's very big, it makes it smaller. Okay. Once again, which of these two is bigger, chi-square left or right? Right. So dividing by a small number, dividing by the left-handed chi-square value, if I take n minus 1 times s squared and I divide by a smaller number, what's going to happen to that value? Does it get very small or stay kind of big? Right. So the right endpoint, the top of my interval estimate for sigma squared, needs to take n minus 1 times s squared divided by the left chi-square value, rather than dividing by the large chi-square value, we divide by the small chi-square value to make this top endpoint of our interval the larger of the two. So our population variance is defined by these two endpoints of our interval, n minus 1 times s squared divided by the right-handed chi-square value, and then the top endpoint of the interval, or a confidence interval, is n minus 1 times s squared divided by chi-square left value. What if we need to find a confidence interval for not the variance, the standard deviation? How are the two related to each other? If you've given the variance and you want to find the standard deviation, what do you have to do? Take the square root. So if I want to write a confidence interval for not the variance of the population, but the standard deviation of the population, I take these two numbers and I square root them. Only difference between this and this is the square root to convert it back from variance into standard deviation. All right. So unfortunately, that chi table that I gave to you guys earlier, the nice one that's laminated, doesn't quite have all the information for both right and left chi values we're going to need for these confidence intervals. So I made a quick chi table here for you. It has more chi values for us to look up. Those you guys want? I got one for you. Did everybody else get one? Okay. Okay. So look at the top row here. Like your original chi table, it doesn't stop at an alpha of 10%. It keeps going further into the other columns here on the left side. 0.995, 0.99, 0.975. No. So the chi table I've given you originally, we could use for a week or so, has these columns on it. What if I need the chi-square left value? For example, what's to the right of this chi-square left cutoff? There's 2.5 here, there's 95 here, so 97.5, 0.975. Do you see a column for 0.975 on this table? Oh, now you have it on this table. It has more chi-square values for us to look up when we create these types of confidence intervals. Or you could just use Google Sheets. All right. All right, so let's try one. Here's a scenario. A random sample of 15 1-ounce silver dollars gives a standard deviation of 0.04 ounces of silver in the coin. Do you think that variance is kind of a big number? When they're minting these coins, they're off by an average of 0.04 ounces from the 1 ounces of silver that's supposed to be in the coin. Your coin might have more silver in it than my coin. That's just unacceptable to me. I want to have the coin with the most silver. So we need to create a 95% confidence interval for the actual variance and standard deviation for the amount of silver in those silver dollar coins. based off of only looking at 15 silver dollars and measuring the amount of silver in the coin, what's an interval estimate for the total variability of the silver in the coin? That's what we're trying to answer. Does that make sense? That argument? Okay. So let's draw a picture. I'm going to draw a chi-square distribution. Two cutoffs. Chi-square left. Chi-square. I'm going to make a 95% confidence interval. I want 95% of the chi distribution to be between those two values, so that the endpoints of my interval capture 95% of the distribution. Now, since your chi table that I typed out to you is defined by the right tail, what part is to the right of my right endpoint for chi-square? What part is to the right?
2.5%.
2.5%. How many degrees of freedom are there in our question? If I looked at 15 silver dollar coins, what degree of freedom are you going to look up?
14.
So for 14 degrees of freedom, what's the chi-square right value that cuts off the top 2.5% from the other 97.5% of the distribution? These are all right tail. Alpha is always right tail. I see 2.5% right here. 14 degrees of freedom. What is that? 26.119. Is chi-square left going to be bigger or smaller? Smaller, because isn't it closer to 0? Chi-square distribution is strictly positive, so the closer I get to 0, the smaller that chi-square is going to become. Now, this is a little bit tricky. It's not like the T or Z distribution, where I have equal parts to the left and the right. It's skewed. So I always look up chi-square with the right tail probability. We know there's 2.5% in this right tail to the right of chi-square right value. We know there's 95% in the middle. So what's to the right of the chi-square left cutoff? Okay, so let's look up 0.975 with 14 degrees of freedom. Degrees of freedom, 14. 0.975, you can see in this column here. Is that 5629? So let's recopy our formula here for a minute. We've got n minus 1 times s squared divided by chi squared right less than sigma squared less than n minus 1 times s squared divided by chi squared left. All right, so let's see here. Let's start putting some of these numbers in. What is n minus 1? For a sample of size 15, how many degrees of freedom on it?
14.
14. We already knew that. It's right here. There were 14 degrees of freedom. So we're going to bring down 14 times what? The standard deviation of those 15 1-ounce silver dollar coins is 0.04 ounces. This is what? The standard deviation or the variance for my sample? Standard deviation. This is S. S equals 0.04. I'm going to not use S. I'm going to use S squared. I'm going to multiply it by the variance of the sample, S squared. This is the standard deviation of the sample, so we take 14 times 0.04 squared. It's a common mistake I see people make sometimes. They just take 14, the degrees of freedom, times S, but it's S squared. You multiply it times the sample variance. This left endpoint, I divide by the chi-square right value. So I'm going to divide by 26.119. Why do I divide by the right chi-square value to make the left endpoint of the interval?
It's bigger, so it'll produce a small.
I've got an interval. Shouldn't an interval be in numerical order? the left endpoint of the confidence interval should be less than the right endpoint of the confidence interval. So to make this left endpoint smaller than the right endpoint of the interval, I divide by the bigger of the two numbers, which is the right chi-square value. We got here 5, 6, 2, 9. Let's get a little calculator. (14 times 0.04 squared divided by 26.119. Was that about 0.0009? Suppose I can get this pulled up on Desmos here. So we can see what we're typing in. So I've actually got it in scientific notation. It's about 8.57 times 10 to the negative fourth. I just moved that decimal place back 4 places. Rather than 0.0009. Let's do the same thing with this one. I'm going to take 14 times 0.04 squared and divide by 5.629. So about 0.004. The variance in the amount of these silver dollars, the variance in the amount of silver in the silver dollars, has to be between 0.0009 and 0.004 square ounces. Variance is measured in square units. When I give the weight of something, do I measure it in ounces or square ounces? I'm talking about the weight of the silver in the silver dollar. Do I want to give the value in ounces or square?
Ounces.
Ounces. Because I had to square something, this is measured in square ounces. So to get it back into more, I don't know, usable units, let's write the population standard deviation confidence interval. What do I do to these two numbers? Square root. The square root 14 times 0.04 squared divided by 26.119 is about 0.0293. Square root of that endpoint of our confidence interval, 0.0631. This confidence interval is not measured in ounces, not square ounces, but ounces. The standard deviation for all the silver dollar coins, amount of silver in them, is somewhere between 0.0293 and 0.0631 with 95% confidence. I'm 95% certain that based off of my sample of 15 coins, I know that the total variance in the amount of silver in the coins is between these two values.